Welcome to All About Atari 8-Bit Programming. We're about to get started in a moment. I'm just going to do a couple more checks here, and then we'll be in business. Okay, we seem to be good to go. If you notice anything awry with the stream, drop a message in the chat and I'll do my best to fix it. This is Brian Jepson with the Rhode Island Computer Museum, coming to you remotely from, surprise, surprise, Rhode Island. And I'm going to be telling you about all the different ways, well, not all the different ways, but many of the different ways you can program old Atari 8-bit computers. This is all the stuff I wish I knew when I was a youngin' and I had an Atari 400. There was so much I did in BASIC, but so much I didn't do in all the other options that were out there. So I'm going to hide my video and get started. Please feel free to ask questions. I will do my best to answer them in real time, but this was not pre-recorded. Some of the video segments were, but my voice that you're going to hear is all coming to you live. And at the end, we're going to share a link for a Google meetup where we can see each other virtually in person. So you won't have to just be staring at me the whole time. I expect this presentation will take somewhere between 30 minutes to 40 minutes, and we'll do a little Q&A in the chat, and then we'll hop over to the Google Meets if you want to join us. So thank you all for being here, and let's get started. So I'm Brian Jepson. Here's an email address that you can reach me at the Computer Museum. bjepson@ricomputermuseum.org. bjepson@gmail.com also works just fine too. And so this image here shows the Atari 800. It was one of the first models that came out. The Atari 400 and 800 came out. The 400 had less memory, had a membrane keyboard, and the 800 had two cartridge slots. Very few cartridges used the right-hand cartridge slot. Almost everything used the left cartridge slot, but the idea was that it would be there for future expansions. Behind the slot there's a area where you can pop up and install more expansion cards as well to expand it. But later on, the computers kind of went in slightly less expandable direction as the design started to look less like something from the 70s and more like something from the 80s. So there are a lot of ways to write code for the Atari, and I've just listed three of them here. There's BASIC, which is the basic programming language that was available on virtually every home computer that was out at the time. Assembler Editor, that was a program that allowed you to edit assembly language programs, which were mnemonics that corresponded to different machine instructions, and we'll see examples of that later on. The assembler editor cartridge would assemble them into binary files that you could then run. C wasn't really a programming language that was enjoyed on the Atari during their heyday. There were languages such as Action that were very close to C, but for the most part, people were using some other language. And there's a link here that links to a list of a whole bunch of different programming languages for the Atari, and I will make these slides available. We'll post links in the recorded video, and I'll also put the links in the chat as well towards the end. So just to set the stage, what's inside this machine? It's got a 1.8 megahertz 8-bit microprocessor, the MOS 6502, which was in all sorts of computers at the time. the Apple II. It was also variant of it was in the Atari 2600. Commodore 64 had a version of it. It was very primitive by today's standards. There was one primary register used for moving things in and out of memory and performing operations on them, two index registers that could be used to specify offsets to activities you were engaging in with the primary register. And to make up for this lack of registers, there was very fast access to the first 256 bytes of RAM, so you could move things in and out very, very quickly if you needed to. There generally is 16K or more of RAM on any 8-bit Atari. That Atari computer that you find, early versions of the 400 had less, but generally 16K or more. In addition to the 6502 microprocessor, there were two graphics processors that worked together. Antic was generally responsible for managing the display memory and manipulating it in various ways. The CTIA and then later the GTIA chips, television interface adapters, they were responsible for conveying the image that the Antic was managing into your television's display. CTIA, GTIA also performed some additional duties such as managing sprites. In Atari language, those were called player missile graphics. These are things like your main character or a bullet that your main character is dodging or shooting. And so the CTIA, GTIA would take care of managing those. Those were generally overlaid on the play field and over the general graphics. There was a dedicated sound and I/O chip, the Pokey. That Pokey managed not just making sound, but also managing I/O with primarily through the joystick port, serial port as well. And we're going to see an example of some cool stuff you can do with the joystick port and electronic components that are pretty easy to get. And so, in fact, you could kind of do Arduino style projects, and we're going to do one in this session. It's kind of fun. So there was a series of 8-bit computers. As I mentioned earlier, the 400, the 800 were first two out the gate. They had a real, very retro look to them. They didn't have built-in BASIC, so you used a BASIC cartridge. And then later came the XL series, and they were pretty much same kind of specs, very close in specs to the original 400 and 800. They were not completely compatible. They had slightly different operating system ROMs and a few other things that were different, but most of the cartridges and disk images you find are probably going to work on anything. The XE series came later. I'm using a combination of an emulator and a real-world 130XE with a whopping 128K of RAM in it in this session here. So if you have an Atari 8-bit, one of the biggest things is you're going to wonder is how are you going to get stuff in and out of it, right? If you've written some code that you've compiled on your computer, or you've downloaded a game or a programming language that you want to run on your Atari, well, I'm going to say you can't just copy it to an SD card and have your Atari load it, but that's not exactly true. There are additional peripherals that you can get that will let you do that. The SIO 2PC is the name of a pretty popular, generally easy to homebrew yourself kind of board that will allow you to use a USB serial or RS-232 serial connection between your computer and the Atari, and this can be used to load disk images, and it's great fun. But I love Fujinet. Fujinet is the adapter pictured here. It has an ESP32 or ESP8266, I can't remember which, with custom firmware on it, a micro SD. So you can not only put things on an SD card, but you can also load things over the network. In fact, you can use native, and you'll see how to do that. You can use native load and save commands and things like BASIC and the assembler editor cartridge to load images onto the Atari. It uses the same port, the SIO port, the serial interface port, that's used by the disk drive and the cassette drive. So basically takes its place. The Fujinet is worth buying. You can get it for $55 with a bare board where you have to 3D print your own case, or around $75 you get a nice case with it. I chose to 3D print my own case, and it looks horrible, but hey, it's okay. It's also open source hardware, so you could build one of these if you wanted to. So I'm going to just dive right into an example on the Atari user interface, where what we're going to do is we're going to boot the Fujinet system. I wouldn't want to call it an operating system, but it kind of is. And we're going to set things up so that a regular Atari DOS 2.5 diskette image has the necessary device driver to be able to use the end drive, which is actually the network device. And then later on, you'll see me use that instead of loading, from D1, which was the traditional disk image. I'll be loading files from a Python server that's actually running on one of my computers here at home. So let's hop into this video right now. So this is what you see when Fujinet boots up. These are a bunch of hosts that you can go to, and I'm just going to pause right here and go back because this video is going a little fast. Oop, okay, getting myself into trouble here. There we go. So the first thing you see when you boot up the Fujinet is a list of hosts. You can just ignore everything I show you here and spend all day going to everything from list to the item in the list from 2 through 6 and just load images, disk images that you find on the internet. It comes preloaded with this list of hosts that are basically file servers full of games and utilities, productivity applications. But what I'm going to do here is I'm going to open up the SD drive, which I have a disk image on, and I'm going to load that disk image. That's Atari DOS 2. Earlier I said 2.5. I really meant 2. I'm going to mount it to the first disk, and then once I've done that, I'm going to go to one of these hosts here where they have a disk image that contains a bunch of utilities. And the utilities I'm using are called Fujinet tools. And so I'm going to mount them to the second drive. One thing I want to call out is that after you make a selection in the Fujinet user interface, you can choose whether to mount something read-only or read-write. We have to mount the DOS disk as write. So back in that earlier step, I had hit W here. I'm loading FNC tools over the network, so I couldn't write to it if I wanted to. The reason we want the DOS disk to be in write mode is so we can copy a file from FNC tools to it. So once that's done, once we've got both of those images mounted, we're going to hit the option button, and that tells the Atari to boot from the disks that are loaded. So these are going to appear to the Atari just like a disk drive. We're also going to hold down option while we're booting so that we bypass the built-in basic. Otherwise, because we're using an XE here, which has built-in basic, we drop into it. So what happens, this is a one-time thing you need to do just to prepare the DOS disk. We're going to copy a file called ndev from the FNC tools disk. We're going to copy that over to D1 as autorun.sys. That's something that gets that's an executable file that'll get run every time you boot, and that'll happen whether you're booting DOS and then going into BASIC, or if you're booting, which we're going to see in a moment. I'm going to power cycle now that I've made that copy. I'm going to power cycle, and I'm going to go back into Fujinet, and now I've got everything mounted. I'm going to press option to boot. This time I'm not going to hold option because I want built-in basic, but I'm still booting with that file system driver. So later on, when we go into basic and want to load something over the network, we've got the capability of doing that. So in addition to using a real Atari, you can also use any of these awesome emulators here. I love Altera, and I'm not sure I'm saying it right, for Windows. It has integrated debugger that's really pleasant to use. I'll get into that a little later when I show you assembly language. Atari 800 Mac X is what I've always used on my Atari, sorry, on my Mac for years. But if you're on Raspberry Pi or another flavor of Linux, you can use the Atari 800, and all these links will be in the in this presentation, and I'll share the link for that in the chat towards the end, so you'll be able to download this. You'll also be able to download code examples and so forth. Another one that's a lot of fun, and I risk losing you because you might go to this website and just start playing with it and ignore me, is 8bitworkshop.com, and I'll show a demo of that later. But it's got it emulates a whole bunch of 8-bit computers. It has assembler, it has C, it has a variant of BASIC, and you can choose Atari 5200, which is a game system that's similar to the Atari 400, or you can emulate the Atari VCS, also known as the 2600, or an 800 XL. So 8-bit workshop's a lot of fun. As you edit the assembly code or the C code or the BASIC code, it will actually recompile it as quickly as it can, and you'll see in real time either things crashing or things working beautifully. Now, finding OS ROMs can be a little bit of a challenge, although there are available, and it's pretty easy to find out how to get them. But Altera comes with a set of highly compatible OS ROMs and also basic ROMs. So they've re-implemented the Atari ROM operating system, which is, the operating system isn't really an operating system. It's a rudimentary set of service routines that support programs that you're running. It's not, it's maybe a little similar to things like CP/M and DOS, but not even with that level of sophistication. But it is there is something there besides just your code running that's baked into the computer. And also Altera has its own version of BASIC, which is very compatible. In fact, I was moving code back and forth between the Altera emulator and the 130XE and had no troubles at all. So first thing we're going to do is a hardware project. This is how to make your own paddle. The reason that I had to do this is, one, I don't have a set of Atari paddles. And one thing to note about Atari paddles is they come in sets of two, whereas an Atari joystick, you plug in the joystick, there's one joystick, there's one plug. The Atari paddles were like a Y adapter. And so two things. I didn't have a set of paddles, and also I wanted to show you how to wire up something directly to the Atari, like a potentiometer. So if you wanted to, say, replace that with a light sensing resistor, you'd be able to do that. So the other reason, even if I did have a set of paddles, I'm not going to tear them apart. An interesting thing, for what we're going to do here, you can't just use an old joystick cable. The reason for that is an Atari joystick cable, if you were to be cruel and cut one off an Atari joystick, an Atari joystick cable does not have all of the pins run to it that the paddle needs. So, but anyways, I don't think you should tear stuff apart. The great news is, guess what? It's just a DB9 connector, the same thing that most of your RS-232 connectors use. So don't rip apart a paddle, don't rip apart a joystick. Just grab a DB9 connector. And you do have to tear the housing off. So I'll show that in some of the pictures here. So I have a potentiometer, 500K to 1 mega ohm, works fine. Push button, I wired it up even though I don't use it in this example. Wire, breadboard, and soldering equipment. So at the bottom shows the breadboard. This is really, really simple. You can also see the pinout for the joystick port, and you can see what I did to the DB9 adapter. The reason I did that is because with the shielding that's normally on it, and the flange is not going to go into the joystick port. You won't be able to get it in there. So tear it apart. Everything will be loose. You have to be real careful. You'll probably end up with a nicer soldering job than mine. But I have something here that's able to go in. I did use a little hot glue to make sure things kind of stayed in place, and so that I could unplug it after I plugged it in. One thing too, don't do what I did. Don't think that because I'm wiring up the female, which goes into the male, that I had to reverse the diagram. I didn't have to do that because the back of the plug, which I was soldering, facing the plug that I'm plugging into, is exactly the diagram I found on Wikipedia. So don't do what I did, and then you'd have to desolder and resolder. So what we're doing here is we're just following the pinout. For the paddle itself, it's just a potentiometer. And so that's going between 5 volts and the paddle A, the first paddle. And so 5 volts goes to one side of the potentiometer, and the paddle A goes to the wiper on the potentiometer. The button goes between pin 3 and pin 8, which is ground. But after you wire this up, test it. Make sure there's no shorts. Make sure nothing's connected to anything it's not supposed to be. You're going to plug it into your Atari, and you want to be careful. You don't want to fry it. If you're really paranoid, you could do what I didn't do, but you could have tried. You could try plugging into your second port. Assuming that your first joystick port. Joystick paddle port is more important than your second one, so if you do burn something out, at least you can still play Defender and other games. So with that, let's look at some basic code. Basic code, this is just a program that would read a paddle, but in my case, it's reading my potentiometer. My potentiometer is electrically the same as an Atari paddle. So first thing we do is we use the graphics command to switch to one of Atari's graphics modes. This is graphics mode 7, a whopping 160 by 96 pixels. They're not really pixels. I mean, they're sort of pixels, but scan lines are in there, so it gets a little complicated. We're also invoking, by adding 16 to it, we're also invoking full screen mode. Otherwise, we would have a small text window at the bottom of the screen. And I'm also using a scaling factor in line 140 for the paddle values, because I'm going to get, I think I'm going to get 0 to 254 from the paddle function, and the maximum is 95, so I have to scale that down. So I'm going to use that Y scale value later to scale the values that are returned. So I have a for loop here. No indentation. We didn't indent stuff back then. You just have to look for the next statement. So what I do is I read the paddle. I'm going to be drawing a graph across the screen continuously. So I have to erase what I drew before, but I don't want to erase the whole screen. That would take forever, and it would look terrible. I also don't really want to, because I'm plotting this left to right, it's going to be in a set of columns. I also really don't want to take the time to clear the whole column. So I'm just going to draw a black line from the top of the screen to where the Y value is. And then I'm going to draw the rest of the line in whatever color 1 is. I think it's kind of a yellowish color. And then I'm just doing this for loop across the length of the screen. And then I go back to the top, and then it starts drawing again from the left of the screen. So we're gonna load and run the basic code, because the emulators are a little bit more convenient to work with. For one, you have a much nicer keyboard to type on than the Atari keyboard. Even though the 130XE was one of the later models, the keyboards still weren't the greatest in the world. But also, this is kind of a cool way to show you how to do things. So I wrote the program in BASIC in Altera, using Altera's BASIC. And I'd configured Altera. You just go into settings, into devices, and you can add drives. And so I mapped drive H to a local folder on my computer, the computer that was hosting emulator. And then I opened a command prompt on that computer. This is a Windows computer, but you could do this on virtually anything. Although Altera, I believe, is Windows only, so you'd have to configure your whatever emulator you're running differently to have a local folder appear as a drive. Well, then I just used Python to run an HTTP server. Now it's just going to serve whatever I had in that folder, which in this case is my saved BASIC file. So here we are. We're in the Fujinet config. I've still got the Atari DOS in slot 1. I didn't bother unloading FNC tools. I'm not going to use them. They just happen to be there. So I'm going to, next thing I'm going to do is hit Option, hold, I'm not going to hold down Option because I want the built-in BASIC. When you're booting XE or an XL Atari, it'll automatically boot into BASIC unless you hold down Option. Sorry, it's restarting this video. So we're going to end up booting BASIC. And now that we're in BASIC, we can use the N drive because we had loaded that file system driver earlier when we prepared the DOS disk, which is in the virtual drive. Now I'm saying load N : HTTP, given the IP address of my computer that's running the Python. And this is why Fujinet is so cool. Loading paddle.bas. And there it is from an emulator to my computer, same code we just saw. And we're going to run it. And as I adjust the potentiometer, you're going to see the graph is going to go up and down. So that could be any kind of analog sensor that you've connected, that you've wired safely to your Atari, and that you've tested and made sure that you're not shorting anything out. I mean, worst case, you'd probably have to replace the pokey chip if you did fry something. I had a problem like this on a Commodore 64 where I burnt out the very, very expensive SID chip, which is not just handles music, but handles joystick I/O. And it turned out it wasn't anything, I was going to say it wasn't anything stupid I did, but the stupid thing I did is I didn't check the joystick I was using. It had terribly frayed cables and it was shorting out. The SID chips are notoriously fragile and they're very expensive. It's why you often will buy a used Commodore 64. And if it's under $100, it probably doesn't have a SID chip in it. That's a talk for another time, though. So we've seen how to program in BASIC and how to move things from an emulator to a real Atari. Next, I'm going to talk about the assembler editor cartridge. The assembler editor cartridge was this mythical thing that my cool friends had. See, I was cool because I hung out with the computer geeks, and then within the computer geek community, there were cooler people, and the ones with the assembler editor cartridge, they were cooler because they could write in machine code. So you can either buy a cartridge. We have at least one in the Computer Museum Learning Lab, or you can just download a binary image of it and boot it in an emulator, or if you're using Fujinet or something similar, you may be able to boot it. But we're also going to talk about cross-assembly, which is probably how you're going to want to do it anyways, but let's look at how it was done back in the day. So I'm going to talk a little bit about the 6502 chip and the instructions that we use. This great image comes from the website listed at the bottom there. What everybody loves about this image is that it shows functional representation of the 6502 microprocessor, as well as which opcodes, which machine language instructions correspond to which part of that. So the accumulator is that general purpose register that I talked about earlier. In the accumulator, you can do comparisons, you can do addition, you can do subtraction, you can do all these various operations. So a lot of time you're going to be using load A, LDA right over here highlighted. I don't know if you can see my mouse. You can't. That's probably an artifact of the full screen mode that I'm in, and I'm not going to try to debug it live. So that's how you know this isn't pre-recorded. So in the accumulator box over in the left, you see an instruction called LDA. That'll load something into the accumulator. Store A, which is that arrow coming out the top, can move information from the accumulator into main memory. Add, see there, we have add with carry. That sets a carry bit if there's an overflow. And then over in the stack pointer box, we have to. I'm not the only one. When I'm writing code, I'm not the only one using the accumulator, right? We've got one register, one general purpose register, so everybody's using the accumulator. Service routines, interrupts. So if I'm doing anything with the accumulator, I have to use PHA, push A, push that guy onto the stack. Then when I'm done, I'm going to use PLA, pull A off the stack. So I have to put the accumulator back the way I found it when I'm done messing with it. And then RTI is just returns from the interrupt. Over down in the lower area, you see we're going to use clear carry. You need to do that. You need to clear the carry flag before you perform an arithmetic operation. Otherwise, you're going to have a bad time. So I'm going to talk a bit about, before this example that I'm going to show you will make any kind of sense, I do have to talk a little bit about the Atari display architecture. So I talked earlier, there's an Antic chip that manages display memory. It also has, it's a microprocessor of its own too. Like the 6502, it has a set of instructions. Its instructions are the Atari display list. There isn't an assembler editor for Antic. You're going to load values into memory. You're going to tell Antic where those instructions are. This is the magic of the Antic is a lot of the magic, enables a lot of the magic that the Atari has, and we'll talk about it. It describes how the graphics are interpreted. This is something that I will personally get confused on a lot. I think I'm not getting confused on it anymore because I've been doing this more lately. But the display list really describes how graphics are to appear. The graphics memory is completely separate. Graphics memory describes what's going to be on the screen. And depending on how your display list is set up, whether that's text or something else, it's going to be interpreted differently. How high it is, how big the text is, that kind of thing. So Atari has this thing called a display list interrupt. Basically, you can write a little service routine that gets called on the periodically. Is it the vertical blank? It's I'm not going to get into how graphics are displayed. What I'm going to do is I'm going to try to explain this a little more simply. It's something that's executed periodically while the display is sort of in between lines, like each line on the screen. So each horizontal line, at the end of each horizontal line, there's a horizontal blank where nothing's being kind of displayed on the screen. So there's these times where this interrupt can run without disrupting what's on the screen, but what it can do is as a screen line is drawn, it can rewrite the display list or make a change to the display list such that you can do more than you could if you were just setting up a display list saying, okay, here's the colors I'm going to use. So you can take 16 colors, you can have a display mode where each line could have 16 different colors on it. And then the display list interrupt, which is getting called not so much in the background, but it's interrupting the processor, running this code, and then going back to your main program. You can change what those 16 colors are. So every line, let's say the screen is 92 lines high. Every line can have a different set of 16 colors. And all of this is happening like while the television's electron gun is zipping across the screen and getting ready to move to the next line. So you can generate all these very cool effects with it. So this is just a small part of a larger assembly language program. The larger assembly language program includes everything needed to configure a graphics mode, everything needed to set up the display list. All this is a service routine. You define it. You tell your in your code, you tell Antic where to find it, and this will get run periodically. So on every horizontal line. So the first thing we do, I mentioned earlier, we push the accumulator onto the stack because we're going to use the accumulator. We have to restore it the way that we found it because this routine is getting invoked as an interrupt. All the other code that's running on your computer has no doesn't really assume this is here. So things have to be put back the way they found them. I'm using memory location 700 as a general purpose storage location. I realized, as I run this code, I actually don't think anywhere in my code I'm actually checking what was in memory location 700. I know from convention that it's a safe area to use, but I'm using it to store a color value. And so I'm retrieving what's in memory location 700. So right off the top, first time this program runs, I'm at the mercy of whatever happens to be in 700. Doesn't matter. It's just a color. It's just going to be our starting color. It could be anything. So we don't really care. So then I'm going to add 2 to that. I'm going to wait. Then I'm going to use this command here, store A, to wait sync. And it doesn't really matter what value is going on there. This is just an action that takes place that tells the Atari, tells Antic to wait for the horizontal sync so things don't get. You've seen old televisions roll, and you've seen weird things happen. Maybe you've even held magnets up to screens. Don't do that; it'll permanently damage them. But all sorts of weird stuff happens because it's essentially electromechanical activity that's drawing. It's not like an LCD screen, an LED screen. And our LED screens are happy to emulate these. I mean, I can plug my Atari into that, but internally these archaic methods of drawing things on screen, these very analog ways of drawing things on screen, are still how an Atari is representing things. So they'll still look the same. And so we're going to wait for that so that things don't get all jittery. We've modified A now. We're going to write that back to memory location 700. So the next time we hit this interrupt, we're going to pull that off. Now, there's an assumption here that nobody else is messing with memory location 700. Pretty safe bet. This isn't a Raspberry Pi where there's like 30 things going on in the background at once. You can pretty much, you can look up at any Atari memory map and you can find locations that are safe. You might even look up an Atari memory map and find out that I chose a totally lame location and that I shouldn't have. So then after we do that, we're going to copy that what's in A to the what's called a background color shadow register. It isn't the actual memory location where the background color is stored, at least that's my understanding, but you write to it, then it gets conveyed over to the background. And it's going to make, this whole thing here is going to make that cool Atari rainbow effect that you may have seen before. And then when we're done, we take A, we restore A to its original state, pull it off the processor stack, and return from the interrupt. So let's have a look. We're in Altera here. I've got some of the disassembly up. I've got an ability to inspect memory locations. So we're in the emulator here. First thing I'm going to do is assemble. I've loaded it into memory. I'm going to assemble what's in memory. I get no errors. Next up, I go into the debugger, and then I tell it to go to 5000, which is where this program starts. And now this does the canonical Atari rainbow effect. You can see in disassembly, there's the subroutine that we just wrote, the display list interrupt we just wrote. And I can also step through it with F8, and you can actually see each scan line and where we are in the scan line. This is amazing. I could put a breakpoint elsewhere in the interrupt, and we'd even see it, in progress. I can also go to that area of memory, 700 or 02 BC in hex, and I can see there I'm incrementing it by 2 each time through. And as you go through this very slowly, now a little faster, I'm just holding down F8, you see how this rainbow effect actually gets drawn. And it's just a very neat effect, but this is happening, this change is happening to the screen as the as I want to say, as the electron gun is scanning across the screen. Of course, this is an emulator running on a computer. There's no electron gun. So cross-assembly is another way we can do things. You can write code on your computer, copy the binary over. This is better. ATASM, it's compatible with the assembler editor syntax. In fact, from the assembler editor cartridge, I use the list command to list it to the P device which Altera is kind enough to just display that on my screen, so I could copy and paste it over into a text editor on my computer, saved it as rainbow.asm, just ran atasm. It defaults to extension .650. I just copy that over to an SD card as rainbow.xex. Xex is a common extension used for Atari executables, similar to .exe on PCs. So now that I've copied it over to the SD card, I put the SD card into the Fujinet, going to boot up the Atari. This time I'm going to go into SD, I'm going to mount rainbow.xex, even though it's not a disk, it's an image. I'm going to mount it into slot 1, and that's going to kick out the DOS disk that was in there, and I'm going to just boot it up. I don't have to hold down option or not hold down option. Same thing. It just bypasses basic when you're booting an XEX from Fujinet. But this is that was running on the 130XE, captured over an HDMI capture. So next is, well, what if we want to compile C code? We can definitely do that. That's no problem. So the CC65 compiler is available for Windows. You can compile it on Unix-like operating systems. And so let's take this is going to be a real brief look through this. A lot of the C that you're going to see in here is generally analogous to what we have to do in assembler. This one is a little different. We're going to use player. We're going to create 2 players, and players are the sprites in Atari. And so I borrowed this from some code. There's I'll just zip back to the top, but you'll be able to see this video. This is a much more complicated tutorial that's really focused on doing inline assembler in C and also display list interrupts. I just happen to like their sprites, and I could read the code, and so I took this code, whittled it down to 1 sprite, and then also changed it so that you could use the joystick with it and move it around on the screen. And I also took out as much of the assembler as I could and replaced it with C, which just to make it 10% more readable. So these hex codes here define the bitmap of 2 sprites that are going to be overlaid on top of each other, so we have kind of nice 2 cool colors. This is the display list here, that it just includes the constants that are needed to specify it. This routine here makes some changes to the display list. Let me just slow down there and explain what that last routine was doing. Make some changes to the display list so that it can it knows where to find parts of the display list. Next, we have a wait for vertical blank. I couldn't figure out how to translate this into pure C. And then next, we set up the player missile graphics by putting it into video memory, putting the actual image into video memory. And then this is the address of, okay, slow down there. Going a little fast here. This is the memory address of, remember, I'm creating 1 multicolor sprite by overlaying 2 on top of each other. So this is the address of player. And all this nonsense here with me having to pause and restart this video, it's only because I could not figure out how to put scrolling text into a Google Slides, and I didn't want to take the risk of bouncing in and out of Google Slides. So really, it's me making my own life more difficult. So this is the address of the sprite. By changing that, you can change where it appears on the screen. It moves very smoothly. That's the thing about sprites, aka players. You're not just copying bitmaps of memory from one place to the other to move things around. Although you notice that I'm not getting into vertical positioning of sprites. They are a little bit more like that. But it gives you that kind of smooth motion that you wouldn't get if you were just drawing on the screen like it were a canvas. So we have some code here that calls the routine to set up the display list. Sort of some housekeeping here. But the meat of it is right here, where we check the joystick. Is it east? Is it west? If it is, we adjust the Y position in the appropriate direction. We wait for the vertical blank. You should try commenting that out. It'll explain why you see so much waiting for vertical and horizontal blanks, because things will just become a mess if you don't. So with this code written, it's real easy to compile it. CL65 with these arguments, and then we compile it to a player gfx.xex, copy it to the SD card, and then we're gonna, just like we did earlier, we're gonna boot this card. We're gonna boot the Atari from SD, booting this image, and here I am turning it on, and you can see the simulcast of the Atari, and there's the player GFX. We're going to boot that up, and here it goes. Now loading, and there he is. Now I pick up the joystick and able to move him around. And because we're just incrementing byte value here, I can overflow and it'll just start back at 0. So whoop, there we go, off the right side of the screen, and eventually come back on the left. There's a bunch of columns on the left that don't actually display. There are a number of interesting idiosyncrasies about the Atari display that you'll learn about as you play with more of that. So let's see. So next up, we're going to check out 8-bit Workshop. Browser-based 8-bit programming, assembler in C. This is just going to be a real, very quick tour. We're going to start out with looking at their webpage. They've got some cool books. Suggest you check them out. They're all, I think they're ordered in possibly increasing order of fun, although I might have the FPGA book be at the end, because that seems the most exciting to me. So you open the IDE, and we're going to look at an Atari 5200, which is architecturally almost identical to the Atari 400. And here we've got a couple of players. Notice the smooth motion, moving around. We can go in, we can look at memory. Over here we see the player missile position changing. We can look at registers. It's a whole lot of fun. And this all just runs in your browser here. Step through it. You can, of course, edit the code if you wanted to. Just run it. There's other examples. There's also C. This uses the same C compiler that we were using earlier, and it's got to compile it. And it's just a demo of some of the different things you can do with display lists. And there are also other systems that you can find. You can also do text-only code in here. And so another game, which is a little bit like the classic Snake game. And then we can also check out Atari 2600. There's a familiar looking effect. I like how it shows the cartridge with the name of program that you're running. It's kind of neat. So that can be a lot of fun. And there's an example of player missile graphics on the Atari 2600. Very long player missiles. Take up the entire height of the screen. Big old sprite. And let's see what else we have here. Oh yeah. Can't finish without some pseudo 3D. If you ever played a game called Night Driver, it looked a lot like this. Well, it didn't have the sunset. Sunset's pretty neat. So let's move on. Now, this is the most fun that you can have without having to turn on a computer. Atari 8-bit bot. Tweet your code to this bot. It's going to try to run it. It can handle Atari Basic, Turbo Basic, Pilot, Assembler, and depending on your perspective, a C or Algol-like language called Action. That is, we didn't have time to get into for this presentation, but it looks like a lot of fun. I never got to use it. So here's their timeline. You can see some of the code that it's running. When you see something running, you can click and see what it's in reply to, and well, there's a whole bunch of code just crammed into one place. There's a really fun 3D pseudo 3D plot here. That's pretty neat. And so yeah, you just tweet, it'll compile it, render a video, and show it to you in the reply. Plenty of other fun stuff. Atari 8-bit bot. Too much fun. Yeah, we got back into a little bit more pseudo 3D stuff. And you can see them talking about getting the action parser working. And there you have it. Let's see if we have anything else here to look at. Oh yeah, pretty colors. And you can see the code for that. You'll see a lot of abbreviations, you know, people trying to cram as much code into a tweet as possible. So we're going to start to wrap up here. There again, I'll make these links available to you. These are basically all the links that I found useful for this presentation. I will say I do have to say something a little bit about Atari ASCII, AT-ASCII. The tricky thing is that Atari has kind of its own weird flavor of ASCII that really isn't ASCII at all. And I'm just speaking slowly because I'm just pasting this link into here. There we go. Now it's in the chat. You should be able to see it. So, you know, when you're moving files back and forth between the Atari, earlier I mentioned that I had used Altera's ability to have a virtual printer device that actually just prints to a little window on your computer to copy and paste things out. That comes out in nice ASCII, but when I'm saving things to my local drive, like and loading them via Fujinet, those are going to be in Atari's own weird version of ASCII. There's a great program called MemoPad, named after what you see when you boot up an Atari that doesn't have built-in BASIC. It's just basically turns into a little bit of a typewriter. And that will allow you to edit your Atari files on your computer. I have a link to Fujinet here, also some links to various cross compilers, and there are also some links to some articles. One article on the display list. But Daybreak Atari is a book that strongly encourage you to check out. It has a lot of it's an in-depth technical manual for programming the Atari that was created by Atari, and it's deep, it's complex, but it'll answer a lot of questions you might have. Also, the Analog and Antic Computing Magazine archives, those are great places to look for code, for tips and tricks. There's also a great display list tutorial here. And throughout this session, I did show how to use Fujinet, which is a little more expensive than just a serial cable like the SiO2 PC connector. If you are using the SiO2 PC, you need some kind of code running on your computer. Respect is a great little program that will allow you to mount disk drives, virtual disks, and present them to your Atari as though they were disks. So, okay, and there's the Google Drive folder link. I thought I pasted it in as myself on another window, but I'm just going to paste it in here. There we go. It's in there twice, possibly. So if you have any questions, post them in the chat. If not, we're going to share a link. In fact, we can move the questions over to that. Here's a link for where we can go hang out and see each other face to face. And let me go paste that into the chat as well, so that I can see you over there. All right. And if you have any, I'll keep this chat window open in case anybody has any trouble getting over there. Thanks everybody for joining us. I hope to see you in the in the after party.